everyone, welcome to today's video on similar figures. So we're going to be talking about similarity. Okay, this is the last lesson in our transformations unit. Love that. We've already learned a ton. We've already learned all about rigid transformations, which are transformations where the preimage and the image are congruent. Our three examples of those were translations, reflections, and rotations. And then we also learned about non-rigid transformations, where the shape and or the size changes. In particular, we talked about dilations, right? We talked about dilations where we have the same shape, but a different size. When we dilate a figure, we are resizing it. We're either enlarging it when it gets bigger, or we are reducing it, making it smaller, and that's a reduction. Okay, and the scale factor is important for that work. So for our key concept in vocabulary today, we're going to be learning about the vocabulary word similar or similar figures. Okay, so generally speaking, more from a definitions perspective, similar figures have the exact same angles. So all the corresponding angles will be the exact same. Okay, so that would make them have the same shape. When two figures have the exact same angles, they have the same shape. And they have proportional side lengths, meaning there's going to be basically a scale factor that we could use to get from one to the other. So very briefly, like if this is my triangle, and this is another triangle, these angles are going to be the exact same. And then maybe my side length here is 2, and my side length here is 4. Maybe my side length here is 3, and this is 6. And this is 4, and this is 8. Okay, the side lengths, there's that common scale factor. I'm multiplying by 2 to take from one to the other. Okay, and all the angles are the same. So those would be similar figures. Okay, and we can prove that two figures are similar to each other if there exists a sequence of transformations, not rigid transformations, but just transformations, which includes translations, reflections, rotations, and or dilations, that maps one figure exactly onto the other. So this is very similar to our definition of congruent figures. Congruent figures meant there was a sequence of rigid transformations that took us from one to the other. All similar means is we're going to include dilations. So we can also resize the shape. In addition to sliding it, to rotating it, to reflecting it, we can also resize it, make it smaller or bigger. All right? So we'll look at three examples today. We're going to start with just understanding similar figures and talk about how we can tell that two figures are similar. Okay, so here we're being asked, is trapezoid ABCD similar to trapezoid EFGH? Note this little squiggly line, that means similar to. So if I look at this shape, I can see the angle B here and angle F. They are telling us those have the same measure, the same angle measure, because they're just drawing that same one line, right? And that happens to have the same angle measure for C and G. That's good, those are corresponding angles. And then a similar thing down here for A and D. A and E, those are corresponding angles. They have the same measure. And D and H, they have the same angle measure. So when I look at this, I see, okay, yeah, these have the same angles, right? Corresponding angles have the same measure. I can also tell that there are like this proportional side lengths, really just meaning that if I can find like a scale factor to get from one to the other. So 20 times 1/2 or divided by 2 gives me 10. Same thing for 28 to 14 and 32 to 16. Okay, so yes, we would say these are similar because they have the two properties that we need. So yes, these are similar, and if these were on a coordinate plane, we could prove that there's a sequence of transformations, rigid and dilation, so not just rigid, rigid and non-rigid, translations, reflections, rotations, and dilations that will map one figure exactly onto the other. All right, so now let's look at an example of performing a similarity sequence of transformations. So we're just being told we have this one shape, here's lots of transformations we need to do to it, combining non-rigid transformations, dilations, and rigid transformations. And then we're going to get a similar figure as a result of that. Okay, so we just have to go step by step. Triangle ABC is dilated by a factor of 2 with a center of dilation at point C. How to dilate a shape isn't the point of this video, so I just fast forward through this. But if you're still struggling with how to dilate a shape, then you should go back to the dilations and puzzle to see that. So when I dilate triangle ABC by a scale factor of 2 and a center at point C, I get this new shape, A prime, B prime, C prime. Okay, that's step number 1. I did that by multiplying all the directional distances, coordinate distances from the center C to the 3 points, and then multiplying that by my scale factor. Okay, so that's my first step. Check. Then it says reflected across the x-axis. So now step 2, I need to reflect across the x. Okay, to reflect across the x-axis, I go the same distance from my line of reflection, but in the opposite direction. So when I do that, I will get right here. This will be A double prime, C double prime, and B double prime. Okay, so check about reflecting across the x-axis. And then finally, they want me to translate 3 units up. Okay, so to do that, we know I take all 3 of the vertices and just move up 3 units, up 3 units, and then I will again connect the points. And there we go, I'll have A triple prime, C triple prime, and B triple prime. All right, so this is now a similar figure. And I'm going to erase that one. And I'm going to erase my middle step. ABC and A triple prime, B triple prime, C triple prime. Those are similar figures because there's a sequence of transformations, which I wrote right here, that took me from one to the other. So those are similar figures. And that's performing a similarity sequence of transformations. And then the last type of question we'll see is we'll be asked, are 2 shapes similar? And we'll need to prove yes or no. Okay, so just like with congruence, our proof when we're trying to prove things are similar is going to come down to whether a sequence of transformations exists. We will always be thinking about the definition of similar figures, thinking do they have the same angles, the same shape, but that's not as technical of a proof. So to prove it, we really want to give an example of a sequence of transformations, if that exists, or conclude no, it's impossible to define a sequence of transformations that will map one shape onto the other. So here is triangle ABC, similar to DEF. So off the bat, we can start thinking of looking at the side lengths, looking at the angles, seeing if they appear to be the same. So I have this AB right here, this length. This is 3 units. AB. AB is supposed to correspond with DE. See, that looks weird, right? We would probably guess it's supposed to correspond with DF, but that's not what this shape is telling us. It's saying, does it correspond with DE? And it's not going to work out because AB is the longest side, right? And that's always going to stay the same if we have the proportional side lengths. AB will continue to be the longest side. So if AB is supposed to be corresponding with DE, then we would think then DE also has to be the longest side, which we don't have. Right away when I see that, I know they're not similar, right? And I can just conclude then that there's not a sequence of rigid transformations that will take me from ABC to DEF. When we said figures were the same shape, we meant that we weren't dealing with the proportions of the side lengths changing at all, right? We might have been splitting or twisting, but we weren't like taking one side length and making it longer and taking another one and making it shorter. Okay? That's not performing any of the transformations that we learned or any sort of transformation. So by the way the corresponding points are set up for us here, we know right off the bat, no, these are not similar. However, it does look like by eyeballing it that triangle ABC might be similar to triangle DFE. And then that appears to take care of the like longest shortest side situation because then AB is the longest side and so is DF in our original one. And then like AC appears to be the shortest one, as does DE, right? So it appears that that's like lining up for us. So what I did is I tried to define a sequence of transformations that maps triangle ABC to triangle DFE to see if that would work. And when I did that, I got really close, but it didn't work out. Okay, first thing I did is I reflected over the x-axis, that's here. then I translated it down 3 and right 5, and then I dilated my shape with a factor of 3, so it got 3 times as big. And I was so close, right? Look at this. I am so close, but it needs to perfectly map onto my shape. In my original shape, F is right there. And my new shape in my image, B is right there. They are 1 unit away from each other. A and D are perfect, perfectly mapped onto each other. E and C are perfect, perfectly mapped onto each other. But B and F do not map onto each other, and the entire shape needs to perfectly map on to the other one following a sequence of transformations. Okay, so that one does not work as well. So thus, I'm even more confident in concluding, no, these are not similar. Their angles aren't the same if we were to actually measure them because of this situation, this angle, and this angle, they're not the exact same. But the best way to conclude it is they are not similar figures. There is no sequence of transformations that will map one onto the other. Great job, everyone. Congrats on finishing our first unit of the year.